Hello everyone, this is ELE3037 pre-recorded lectures section 6, in which we will continue our discussion about receiver non-linearities. So the topic that we will discuss now is receiver sensitivity. So the sensitivity of an electronic device refers to the weakest input signal required for a specific output, and generally the specific output that we are interested in is enough signal power so that we can make sense out of received signal. The sensitivity of a receiver is the minimum RF signal that can be detected at the input to the receiver with acceptable signal to noise ratio. So imagine if we have one receiver with multiple electronic high frequency systems and we have one antenna, then we are actually interested in the minimum signal to noise ratio at this stage, for which we can get signal that is powerful enough that our detectors or our analog to digital converters can actually make sense out of it. So receiver sensitivity is generally defined as the power at the input here, not at the output of the receiver, because receiver also has its own noise figure, it also has its own equivalent noise temperature, it also has its intermodulation distortion products, and it has a definition of power of third order intercept point. So all these definitions actually impact the signal that is received here. So we are interested in whatever we will get out here should be readable by the detector. So whatever power we need for that at this input side is what we are interested in. The noise can sometimes be so high that it makes or obliterates the desired signal. A large signal will be well above noise and is easily recognized, amplified, and demodulated. So if at the receiving side, or after the antenna and before entering into the receiver circuit, if our power is high enough, then receiver will easily amplify it and will be easily the signal will be easy to demodulate. A small signal will be barely larger than the noise, so may not be successfully received. So imagine if I received a signal to noise ratio at this point, which is almost equal or very less have very less power above the noise floor, then it will be very difficult for me to actually pass it through my receiver circuit and then to be able to make sense out of it. It may get lost inside the receiver as well. So the receiver sensitivity, from the noise notes, we already have seen that noise ratio is actually the signal to noise ratio at the input divided by signal to noise ratio at the output. I will draw a simple receiver block here again. So the signal to noise ratio at the input divided by signal to noise ratio at the output is actually what we call noise ratio, and it's equivalent to noise figure in dB terms. So rewriting it as P signal divided by PRS. So imagine that whatever is here is actually equivalent to a simple resistance or a simple equivalent resistance. So whatever the noise power is generated by this resistance can be described as PRS, or equivalent resistance noise, and P signal is actually the signal that we will get at the input. So P sig denotes the input signal power, PRS denotes the source resistance noise power, both per unit bandwidth. So both of these terms are per unit bandwidth because we know that we are concerned about our signals and our noise power in a given bandwidth rather than the entire wide band of application. Therefore, rearranging P signal is actually equals to PRS, that is a noise produced by the equivalent source resistance multiplied by noise ratio, that is an R that actually depends upon this receiver, the quality of this receiver multiplied by signal to noise ratio at the output, that is we are interested in, required signal to noise ratio at the output. So therefore, for a channel with a flat frequency response bandwidth, having a bandwidth that's almost flat, then P signal will be equal to PRS multiplied by NR multiplied by bandwidth here, because we previously talked about P signal per unit bandwidth, but now we are actually putting this bandwidth inside our equations multiplied by signal to noise ratio that is required at the output of the receiver. This equation predicts the sensitivity as minimum input signal that yields a given value of output signal to noise ratio. Changing the notation slightly and expressing the quantities in dB. So P in minimum required power at the input of a receiver is actually equal to the noise power in dBm plus noise figure of the receiver plus 10 log bandwidth plus the output minimum signal to noise ratio that is required for us to make sense out of a signal, where P in minimum is the minimum input level that achieves the required signal to noise ratio at the output of the receiver. B is expressed in hertz, that we already know. So generally at room temperature, PRS is equal to KT, that is almost minus 174 dBm per hertz, and if you want to include hertz, then we will just add plus 10 log of B. So actually P in is equal to 174 dBm, that is minimum noise level, because of the movement of particles inside any system, plus noise floor of the receiver, plus 10 log of bandwidth. So all of these terms are actually defined to be as a noise floor, plus the minimum signal to noise ratio that is required at the output of the receiver. Notes: now the sum of first three terms is the total integrated noise of the system and generally is called noise floor. When 3 dB is added to noise floor, this condition is known as minimum discernible signal. Now this is important. Minimum discernible signal is actually addition of 3 dB into the noise floor. So if my signal is 3 dB above noise floor, it means that signal is called minimum discernible signal. So just to draw a little bit on spectrum, imagine in a frequency response, this is my noise floor sitting at around minus 140 dBm. If I get a signal as small as minus 137 dBm, I will call this signal as minimum discernible signal. So any power above this signal is good for me. My receiver can actually detect what is received. But if my signal goes beyond this 137 dBm point, then it will be outside my minimum discernible signal level. So when 3 dB is added to the noise floor, this condition is known as the minimum discernible signal level, and this is normally used as the working noise floor definition in real communication system designs. That is, signal must be 3 dB or have at least the same power level as the noise above the noise before they can be readily processed. So for example, if I work out these values in kind of watt, so imagine I have 10 microwatt of signal is the level of noise, then I need at least 20 microwatt of signal to be able to make sense out of it. So that's kind of a general in terms of linear scale, this is kind of a general definition of minimum discernible signal. So there's a graph of real application system in which a base station antenna is actually receiving multiple signals in LTE band and GSM band that are transmitted by different multiple radio transmitters. So here we can see that our noise floor is almost at the level of 0.01, that is very low. So whatever we can receive that is 3 dB above this level should be readily detectable by the receiver. But as you can see, the signal that we receive in LTE band is pretty high power. Plus the signal that we receive on multiple channels of GSM is also pretty high power. So these signals are detectable by the receiver. So the minimum receivable signal is actually defined at the input of the receiver, not at the output. So this signal is at the input of the receiver. So perhaps there is a possibility that after passing through the receiver and after the amplification and after everything else, we may get this received signal to be detectable by whatever is coming after our receiver, that is generally analog to digital converters.